Okay, let's look at some examples of actually calculating some vector products. In this example, we've got two vectors, 6i hat minus 3j hat plus 3k hat. I'm using the ijk notation again, so let's look at vector b. That's going to be 3i hat plus 2j hat plus k hat. And of course, we know there's an understood number 1 in front of the k hat. So to take the vector product, we want to form the components first, I hat, j hat, k hat. That goes with x, y, and z, so all in a row. And then I take the components of the first vector, 6 minus 3, 3, and then the components of the second vector, 3, 2, and 1. 3, 2, 1. And of course, this is going to be equal to the vector A cross B. So when we look at this, we can take the first term, I hat, and of course we cross out the column and we cross out the row, and we have I hat minus this subdeterminant. And so when we calculate that out, I get minus 3 times 1, minus 3 times 2. We plug these in and we get minus 9 in the I hat, or the x direction. Then the next step, we move our cross out over by 1. We have our column downward, and this is going to be j hat, and we've got 6 times 1 minus 3 times 3, and I made a mistake. Uh-oh, do you see the mistake that I made? I forgot to put in my minus sign. Remember, when we move this guy over, we have to alternate the minus sign. So this really should be minus j here. This is one of the most common mistakes that you can make. So, gosh, it's good that I made that mistake so that I could point it out to you. Now, that means that this answer is going to be plus 3i hat. And I'll change that in my answer down below, just so that we don't forget to do that again. But remember, every time you move the cross out over to a column, you want to alternate the sign. So when I move it over for the third term, the k hat term, I cross out this column and this row. I'm left with the determinant 6 times 2 minus 3 times 3. This minus and that minus together will give us a plus, so I get 12 here plus 9, and that gives me 21 in the k hat. And so that gives me an answer for A cross B of minus 9i hat plus 3j hat plus 21k hat. Let's look at another example. This one's a little bit more challenging. So the question is to find two unit vectors that are orthogonal. That's a fancy word that means perpendicular, that are orthogonal to the vectors A is equal to 2, 0, 3, and B is equal to minus 1, 4, 2. Now, of course, that 2 would be the x component, the y component, the minus 3 would be the z component of the vector A. That's another way of writing vectors. You don't always have to put in the hats, but sometimes I just like to mix it up and show you guys different ways of doing things. So we want to find two unit vectors. Remember, what's a unit vector? No, come on, say it out loud. What's a unit vector? It's a vector whose magnitude is equal to, hopefully you're saying 1 right now. So that's right, it's a vector whose magnitude is equal to 1. And we want to find it's orthogonal to both A and B. Or another way of saying that, it's perpendicular to the plane that contains both the vector A and the vector B. So how are we going to do that? What's our strategy? Well, we know that the cross product or the vector product of any two vectors will be mutually perpendicular to those two vectors, or perpendicular to the plane that those vectors lie in. So we can say that the vector product is going to give us a vector that is perpendicular to both A and B. So I can do either A cross B or B cross A, and I'm going to end up with a vector that's perpendicular. Once I have a vector that's pointing in the right direction, I can form the unit vectors using what we know about unit vectors to point in the same way. So let's just go ahead and do that, and hopefully it will make sense. So just for fun, I'm going to use the alternative method, the crisscross method. And so I'm going to have my cross product, A cross B, and I'm going to set up my determinant with the unit vectors, the components of A, and the components of B. I'm going to use the other method, so I'm going to duplicate the first two columns. So this is x2, -1, x2, -1, y0, 4, duplicated over here. And then I simply take it and I do my crisscrosses. And so I go forward, so that's x hat times 0 times 2 gives me 0x hat. Y hat times -3 times -1 gives me 3y hat. Z hat times 2 times 4 gives me 8z hat. And then I go backwards, and remember with the backwards sign, with the backwards strikes, you get a negative sign. So that's 2 times 2 gives me 4, but it's going to be minus. Then with the x hat, I get 3 times 4, that's -12, but again, it's a backward slash, so you get another minus. A minus times a minus makes plus, and that gives me 12x hat. And then my z hat times 0 times -1, that's going to give me 0z hat. I add all these together, I group the like terms. Now we have to be careful because this 0x hat goes with the 12x hat, not the 4y hat here. So we have to group like terms. We have to be very careful. And so we've got -4y hat and 3y hat gives me -1y hat. 8z hat minus 0z hat gives me 8z hat. And of course the x hats, I've got 0 plus 12, and that gives me 12x hat. And so my answer works out to be that A cross B is 12x hat minus y hat plus 8z hat. And that is a vector that is equal to the cross product of A cross B, but we also know that that is a vector pointing in a direction that's perpendicular to both vector A and vector B. Now, if we know that the two vectors that are perpendicular to the plane formed by A and B are A cross B and B cross A, we can form two unit vectors along those directions. Now, we have C equals A cross B, and that's just what we calculated, but any vector C can be written as the vector C equal to the magnitude of C times the unit vector that points in the direction of C. And so if we want to find the unit vector, we can just divide both sides by the magnitude of C. That'll get C hat by itself. And so C hat is equal to C vector divided by C magnitude. And so all we have to do is calculate C magnitude and divide it into the C vector components, and that'll give us a unit vector pointing in the direction of C. Remember, this guy C hat is a scalar. So anytime you multiply a vector by a scalar, you change the length, but you don't change the direction. So we know the direction of this guy is perpendicular to A and B, so that means the unit vector will also be perpendicular to both A and B. Now we just calculated that C vector, or A cross B, is equal to 12x hat minus y hat plus 8z hat. We use the three-dimensional Pythagorean theorem. We plug in the components, square it, and then square them all, add them together, and then take the square root of the sum, and we get 14.5. Now this C vector, I want to divide every term by 14.5 because C hat is C divided by C magnitude, and when you do that, you get this is the answer, 0.828x hat minus 0.069y hat plus 0.552z hat. And of course, if I simply multiply everything by a minus sign, that would give me the unit vector pointing in the other direction, 180 degrees away from the first vector, perpendicular to that plane. Now, if I wanted to check that this really was a unit vector, all I have to do is take its magnitude, and if you do that, you'll see that the magnitude of C hat does in fact turn out to be 1. You know, it might be 0.99899 or something like that with rounding, but effectively you're going to see that it is 1. Let's look at one more example. We want to determine the vector v dot the vector w cross v. That is the scalar product of the vector v with the vector with the vector w cross v. Now, you could do this the hard way. We could write out all of these vectors in terms of generic components. So we could say that v is equal to some Vx in the x hat direction plus Vy in the y hat direction plus Vz in the z hat direction. I'm falling asleep writing all this out. It's so tedious. But I could do the same thing with W, and then I could set up the cross product of those two vectors, W and V, and then I could apply the rules and do the scalar product. But I'm lazy. Do I really want to do all of that? Probably not. Nope. I'm pretty sure definitely not. I don't want to do that. Is there maybe a shortcut? Can I get the answer to this faster by being a little bit clever? Maybe so. Let's see. What do you know about the vector that's formed by the cross product W cross V? We know a lot. We know it represents the magnitude represents the area of the parallelogram. We also know that the direction is given by the right-hand rule, and that direction is going to be perpendicular to both of these vectors. So whatever W cross V is, it's going to be perpendicular to W, and it's going to be perpendicular to V. And so what that means is once we take this cross product, we want to take the dot product or the scalar product of a vector that is V with another vector that is perpendicular to V. In other words, the cosine of the angle between the vector formed by this guy is 90 degrees from that guy. Any two perpendicular vectors have a scalar product that's equal to 0. That's the rule, because the angle between them is 90 degrees. And we can write out V vector magnitude times the magnitude of W cross V, whatever that vector works out to be. So it's that magnitude times the cosine of the angle between them, which is 90 degrees. And of course, the cosine of 90 is 0. So the whole thing, this whole thing here, is just 0. And so we don't have to multiply all these terms out, but if you do, you'll see there's plenty of cancellations and everything will cancel and you'll end up with 0. If you're feeling particularly masochistic today, you can try that, but I guarantee you that it'll work. But give it a shot if you don't believe me. Anyway, this is some examples on the vector cross product. Now let me show you, on the next slide I want to go over again some of the properties that we see. So here we have just some things to look at. So again, if S is a scalar, we can have S multiplied by the cross product A cross B. And this is a little bit weird, but it's an important rule. If I bring the scalar inside the parentheses, it doesn't get distributed to both of these. It only gets distributed to one. So S scalar times the cross product A cross B is the same as S times A then crossed into B, or A crossed into S times B. If you distributed them both SA cross SB, that would basically be like multiplying it by S squared. And so you want to make sure that you're very careful when you do those kinds of distributions. Now, another important idea is something known as the triple product. If I take A cross B cross C, that's equal to the B vector times A dot C minus the C vector times A dot B. This is sometimes called the back cab rule to help you remember the orders, but A cross B cross C is B vector times A dot C minus C vector times A dot B. This is also known as a triple product. So this is A cross B cross C. So we're crossing three vectors together, and that's the triple product. Just like we saw with the scalar product, this next one shows us that if I take a derivative, you simply do the normal product rule. So it'd be the derivative of one crossed into the other plus the derivative plus the one crossed into the derivative of the other. So that's the product rule for differentiating a vector product. And then the last thing that we can say is if I have A dotted into B cross C, this is another kind of triple product. So I've got B cross C is going to give me a vector, and then I take the scalar product with A. That's going to give me a number, so the scalar product is always going to give me a scalar. And of course, I can reverse the order of these. I can do A cross B and dot that into C. Either of these triple products is going to give me the volume of the parallelepiped. So this is, you can see I've drawn in the parallelepiped formed by these vectors. And it got cut off on my picture here, but this vector here would be A. This vector here, I don't know if you can see that, that one would be B. And this vector up here is C. That's the C vector. So A and B make a plane, and then C is at an angle to those, and you can see that the volume of this shape is given by this triple product. And this particular shape is called a parallelepiped. And if you have a cube or an elongated cube, more like a three-dimensional rectangle, those are special cases of parallelepipeds. But this is sort of a general idea of a parallelepiped. And this particular triple product will give you its volume, which is kind of cool.